Welcome back, everyone. We're now going to begin a quick series of lectures that are just briefly going to go through the steps of building up to full cross-validation. Keep in mind, a lot of these topics we've already discussed before, so we're not going to dive too deeply into the details. Let's begin with a classic train test split that we're already familiar with. Recall, for a train test split, you begin with the entire data set. You choose some percentage to be test and some percentage to be trained. Typically, it's going to be a 70% training set, 30% test set, or somewhere around there. And then what you do is you train the model in the training set and then evaluate the error on the test set. And then what we allow ourselves to do for the classic train test split is do model adjustments, such as adjusting a hyperparameter based off the error from the test set. So keep in mind, we're fitting the model to the training set and then evaluating the test set, and we do allow ourselves to adjust hyperparameters based off the error or performance from the test set. So what we're going to do is just briefly review this process in scikit-learn, and then later on we're going to expand this until we reach full k-fold cross-validation using the generalized scikit-learn functions. So let's head over to a notebook and quickly work this out. Alright, here I am at the Jupyter notebook. I've already done a little bit of work. I've imported NumPy, Pandas, Matplotlib.plyplot, and Seaborn in case we need them. And then I've read in, underneath the data folder, there is the original advertising.csv file that we're already very familiar with, and it has the TV spend, radio spend, newspaper spend, and sales spend. And all I'm going to do here is I'm just going to do a quick reminder of the classic train test split procedure, where we clean adjust the data as necessary for both x and y. In this case, it's kind of already set up. We're just going to split it into x and y. That's the next step. Split the data then after that into a train test set for both x and y. Then we'll scale the data, the training x data, and then we will scale also the test data, create a model, fit train the model on the x train data, evaluate the model on the x test data, and then we'll create predictions and compare it to y test, and we adjust parameters as necessary and then repeat steps 5 and 6. If you already feel very comfortable doing this with Python and scikit-learn, feel free to move on to the next lecture. However, it's probably a good idea just to have a quick review of how to do this, since it has been a while since we actually dealt with a data set and ran a model. So let's just quickly go through this as a quick reminder. Always good to get a little bit of practice in. We'll say x is equal to df, and I'm going to say drop sales along axis is equal to 1, because I know that my feature set is just going to be TV, radio, and newspaper. We'll go ahead and run that, and now let's define our y. So y is equal to df sales column, and we've kind of figured out what's features and what's y. Next step is to perform the train test split. This is quite simple to do. We say from sklearn.modelSelection import train test split. And as I've mentioned many times before, my favorite way to do this, Shift Tab, come down on train test split until we find xtrain xtest, ytrain ytest. Copy this in and go ahead and paste it. And then what we're going to do here is just choose some values where we pass in our x features, our y, and then we pass in our test size. In this case, we'll go ahead and choose 30% test size. And if you want to get the exact same split I do, you can go ahead and choose the same random state I do. And in this particular case, I will go ahead and choose a random state of 1. So we'll say random state is equal to, actually let's go ahead and choose 101, just so it matches up with the notebook. So we'll choose random state of 101, test size of 30%, pass in your x and y, run that, and we've completed the train test split. So in general, you don't know if the units of TV, radio, and newspaper are the same unless you have some sort of description. And if they're different units, then it's going to be difficult to compare the coefficients. So when it comes to something like linear regression, it's probably a good idea to scale the data. Keep in mind, we've already had a discussion on scaling data previously, so we're just reviewing by this point in time. To scale data, what we can do is say from sklearn.preprocessing import, and there's many different ways to scale or normalize data. We're just going to say import standard scalar. Recall that we create the scalar first, so standard scalar, an instance of it, and then we'll say scalar fit, and this is where you should be reviewing your previous notes, but recall we only fit to the training data because we want to prevent data leakage. I don't want to assume prior information about the test set. Once I fit to the training data, I'm going to say my new xtrain is equal to scalar transform xtrain, and then my new xtest is equal to scalar transform xtest. Perfect. So we've completed a lot of steps already. We did step 0, step 1, step 2, and step 3. Now it's time to create the model. Let's go ahead and choose a ridge model. That way we actually have hyperparameters to adjust. So we'll say from scikit-learn.linearModel import, and notice what I'm going to do here. I'm just going to import ridge, not ridge-CV, because I intend to slowly, throughout this kind of lecture series, slowly adjust how we're working with our cross-validation methods with ridge. So this way, this can generalize to any model algorithm within scikit-learn. So I import ridge, and now it's time to create the model. So I will say model is equal to ridge, and I'm actually going to choose kind of an extreme alpha value to display the fact that I can adjust hyperparameters later on. So go ahead and choose alpha 100. It's probably not a great choice, but it's kind of on purpose right now. So I choose my hyperparameter value, create my model, and then the next step is to fit my model on the training data. So we say xtrain and ytrain. And then I finally get my predictions. So we'll say ypredictions or ypred is equal to model predict. And hopefully all of this feels really familiar by this point in time. And we'll say predict on the x test. Now it's time for evaluation. Many different ways we can evaluate this. I will go ahead and just use mean squared error. So we'll say from sklearn.metrics import, and we'll say mean squared error. And let's go ahead and calculate the mean squared error of our model. ytest, ypred, and right now my mean squared error is 7.34. Okay, so what have we done so far with the train test split procedure? I know I'm going through this pretty quickly, but this should all be reviewed by this point in time. I've done the scaling, creating the model, fitting and training the model, and then it's time to evaluate the model. And the next step would be to adjust parameters or hyperparameters as necessary. Now, what I need to do is figure out if there is a better value of alpha. And when I'm just doing a simple train test split, I'm really limited here. What I would need to do is maybe create some for loop that checks out a bunch of different alpha values, but essentially, if I'm train test split, I'm kind of just going to guess and check, which means we'll have to go back and create another model. So we'll say something like model 2 is equal to ridge, and now I'll choose a different alpha parameter. And this is known as adjusting the hyperparameters based off your test set performance. So I'm hoping to improve on 7.34. And maybe I kind of read ISLR and I realize I should have chosen a lower alpha value. So I create model 2. We'll go ahead and fit again to the training data. So we'll say fit on xtrain, ytrain. And then what we're going to do here is get new predictions. So we'll say ypred2 is equal to model2.predict off x test. And then finally, let's calculate the mean squared error based off the ytest and ypred2. Run that, and clearly this alpha value has now performed better. All right, so what are the advantages and disadvantages of a simple train test split? Why don't we just always do the train test split? Let's start with the advantages. The main advantage here is that it's actually very simple to understand what we're doing. All we're doing is we're separating out our data set into two sets. That way I can fairly train and evaluate my model. And recall that we essentially just do this with one line where we only do the split once, which also saves on computation time. If we had a very large data set, it's not really hard for the computer to just split it up 70-30% split. So that's really easy, and that's a major advantage. The other advantage here is that it's just very simple and intuitive to understand what we're doing. We're just splitting it up, train it on, fit it on one set of data, and then evaluate it on another. So now let's begin to talk about the disadvantages to this. I think one of the disadvantages here is just actually trying to get the optimal hyperparameter value can be quite tedious. Clearly, I could just run a for loop to try to check many alpha parameters here, and at a certain point that will essentially turn into a grid search, which we will learn about later on in this section of the course. But it is a little tedious to constantly have to create a new model and then check another alpha parameter, fit it, predict it, and repeat this process over and over again until suddenly I'm satisfied. So it's a little hard to tell what the optimal value will be right off the bat. Clearly, there's a little bit of tedious code here to keep repeating this. More importantly than that though, I would say the major issue with this is this mean squared error of 2.31 is not the most fair evaluation or report of this performance metric we could possibly do. And why is that? Well, technically speaking, when I get mean squared error of 2.31, this is not the first time that this model has seen test. Yes, technically model 2 has never seen x test before, but I did adjust alpha is equal to 1 based off x test before. So in a way, while this model has technically never seen the test set, we already know that its hyperparameters were adjusted based off test set performance. So it's kind of a little bit of this hidden interaction of knowledge from the test set. And is that the most fair evaluation of a model? Not really, which is why for the next step, it would be really nice if we could hold a little bit of data aside that the model is never adjusted to or fitted on to get some sort of final performance metric that I know is a very true and fair evaluation of the model's capability. So let's move on to that, which is going to be the train, validation, test split. Very similar to this, but we just add an extra split as a holdout test set. I'll see you in the next lecture.